Okay, so let's do another example problem. This is actually one that I think is kind of cool because it doesn't look like a rocket equation problem, but it is. So let's say that you have a wagon here, okay, and you are pulling your wagon. Okay. So you're pulling your wagon and you're walking along pulling it at 67 centimeters per second. Okay. So you're not walking very fast, you're walking slowly, pulling the wagon, and somebody is pouring sand onto your wagon as you're pulling the wagon. And so they're pouring sand onto your wagon at a rate of dmdt 4.1 kilograms per second. And so the question is, how much force do you have to be pulling? Well, sorry, let's make it 14.1 kilograms per second. So how much force do you have to be pulling here in order to keep this wagon moving at constant velocity? And so you look at it and say, well, you know, R relative velocity equals the rocket thrust. Well, hang on. This R is minus dm dt, relative velocity equals ma. So this is your force. Okay, so what's happening is, as this mass is going on here, we have a positive dm dt. We're adding, so that gives us a negative acceleration. So that means as this wagon is rolling along, as you're pouring stuff onto it, it is slowing down because you have a negative acceleration, which means you have to provide a force this way to balance that to keep it going at constant speed. So that means that the force you provide is equal and opposite to that, so that's going to be equal to the minus ma. So that means the force you provide will be dm dt times the relative velocity. Okay. Well, what's the relative velocity? Well, the relative velocity is, as the wagon is going along, as the stuff is pouring onto it, it's coming straight down, but the wagon is moving with some velocity relative to that stuff. So that's your 67 centimeters per second. That's 0.67 meters per second. So that means the force that you apply is going to be 14.1 kilograms per second times 0.67 meters per second. And so the force that you apply is going to be equal to 9.45 newtons. So that's how much force you have to apply. Now, this does not look at all like a rocket. Well, it's not a rocket, but we still use the rocket equation to solve this problem. In fact, the rocket equation is used for a great many things. For example, you have a squid, and so you got the squid, and so you got the squid here. Okay. So the way the squid moves is it has a whole bunch of water in here. It swells up and it squirts the water out furiously out in this direction. And so we have dm dt of water coming out, which pushes the squid that way. And so, well, squid motion or octopus motion, that's also, even cuttlefish motion, that's going to be also rocket equation stuff. Now you got a little bit extra stuff in there because you got the drag forces and things from the water, viscosity, but you have other sort of factors in there. Another example using drag forces would be an aircraft engine, a jet engine. So you have a jet engine, and so the jet engine, basically you've got fuel mixed in here and it goes spewing out the back, and it comes out the back faster than it goes in the front, and so that means that you have you have bigger velocity out the back, and therefore you get thrust. So this is jet engine thrust, and so all this relates to the rocket equations.